Hello there, students. In this video, we will be continuing our discussion on one-dimensional kinematics by introducing the following topics: time, average velocity, and average speed. In a 400-meter dash, all the athletes have to complete the same distance, but we use the measurement of time to determine who wins the race. We're interested in the change in time, or how long something takes to transpire. If we label the moment their feet begin to move as t0, or t sub 0, and the time they pass the finish line at 400 meters as their final time, or t sub f, then the change in time, delta t, is equal to t sub f minus t sub 0. This should look very familiar from our last video, where we had a change in position, x sub f minus x sub 0, which we called displacement. To simplify things, we usually take the initial time, or t0, to be equal to 0 seconds, so that our change in time equation looks like this. From here, since we're only dealing with one time variable, t sub f, we can drop the subscript and let t sub f just be written as t. If one runner makes the 400-meter dash in a shorter period of time than another athlete, we say that they were going faster. We can put this idea of going faster into an equation by defining velocity. The average velocity is defined as the change in position, or displacement, divided by the change in time for that displacement. For an average quantity, such as an average velocity, we use a bar over the letter to distinguish it from other similar quantities such as an instantaneous velocity. Since displacement is a vector, this makes velocity also a vector, meaning it has a direction as well as a magnitude. Consider two people passing each other on a sidewalk. We have to choose a positive direction and a starting point for our coordinate line. We'll choose to set our 0 at the left person and the positive direction to be to the right. If the blue person makes their displacement in the same time it takes the red person to make their displacement, which is t equals 3 seconds, what are their average velocities? With our coordinate line, we see that the blue person took 3 seconds to make a displacement of negative 6 meters. Putting this into our equation for average velocity, we find that they have an average velocity of negative 2 meters per second. The red person similarly takes 3 seconds to make a displacement of positive 3 meters, making their average velocity equal to 1 meter per second. We can take a look at position as a function of time on a graph to understand a little bit more about velocities. As an example, if you are walking down a city street for a few blocks non-stop at a constant speed, your position versus time graph might look like this. But more realistically, you'll have to stop and wait for a crosswalk light, or maybe you happen upon a friend and talk for a moment. Then your position versus time graph might look like this, where your position stops changing for periods of time as you wait or talk, and then start moving again. In the end, though, an average velocity only takes into account the beginning and the end points, so it's possible that both of these scenarios would give you the exact same average velocity when calculated, even though the trajectories are very different. In general, a position versus time graph is just a curve like this. This is a position function and is labeled as x of t because the position x is a function of time t. All the average velocity is telling us is the slope of the line between 2 points, since slope is the change in the y-coordinate divided by the change in the x-coordinate, which is exactly how we define velocity, the change in position, our y-axis, divided by our change in time, our x-axis. If we wanted to know the velocity at one exact moment in time, we'd have to move x0 and x sub f closer and closer to that point in time of interest, until eventually we reach the realm of differential calculus where we'd have to start taking limits of functions. We won't be going into that in this video, but if we did, we'd arrive at the instantaneous velocity at that point in time. When we introduced displacements, which are vectors, we found a scalar quantity to go with that, which we called distance. Similarly, for velocities, which are vectors, there is a scalar quantity as well, which we call speed. Speed is what is measured in your car's speedometer, Your car doesn't know what direction it's traveling, so it can't report a vector quantity like velocity. It only knows how fast or at what speed you are traveling. The average speed is sometimes written as the absolute value of a displacement divided by the time it takes to make the displacement. This is a little tricky because to calculate an average speed, you need to know the total distance traveled, and taking the absolute value of the total displacement might not be correct. Let's illustrate this with an example. For this final example, let's consider a baseball player who just hit a home run. Starting at home plate, they round all the bases, covering a total distance of about 100 meters, ending right back at home plate 20 seconds later. What is their average velocity for the entire run, and what is their average speed for the entire run? For the average velocity, we need the total displacement, which, because the player starts and ends at home plate, their total displacement is 0. This means their average velocity is also 0. Since velocity is a vector, we can split up the run between each base as a separate vector. In this way, we can see that the run from home to first base is in one direction, and the run from second base to third is in the exact opposite direction, with the exact same magnitude. This means the vectors cancel each other. The same happens when we look at the vectors between bases first to second, and then from third back to home. Since all the vectors have another vector that cancels them out, we see that the answer should indeed be 0 as we calculated. Now, for the average speed, we need the total distance traveled, which is 100 meters, divided by the time taken to travel that distance, which was 20 seconds. Putting that all together, we get an average speed of 5 meters per second. So to recap, in this video we learned about time, velocity, and speed in one-dimensional kinematics. Thanks for watching and learning about physics. If you have any questions, please post a comment on the video or on my Facebook page in the video description.